So the Martin B. Hickman Outstanding Scholar Award is the most prestigious award that we have in our college for scholarship. So Dean Hickman was the dean for 17 years of our college, and I'm pretty sure I said the same thing last year, but with every year that goes by that I'm the dean, I'm just more and more impressed that he did this for 17 years. But we can feel the spirit of the foundation that he built for our college as we go about our work. We're so grateful for him and the contributions that he made to our college and to our students. So because of that, we give this award every year, the Hickman Distinguished Faculty Award, to a faculty member whose professional accomplishments really display excellence. So this year, our award recipient is Dr. Matt Bekker. He's from the geography department. I also want to acknowledge his family. So we have his wife here and her parents, and then Dr. Bekker's parents, and I think a daughter and some sisters. Okay, so we've got, second row is the Bekker row. So we're really grateful that they can be here. Welcome to you all. Support Matt today. We're going to start out by hearing from a word from Dr. Hickman's daughter, Melissa. So we're going to have her come up here in just a minute, and then after she speaks to us a little bit about her dad, we're going to hear from Dr. Perry Harding, who he's a professor in geography, and he'll introduce Dr. Bekker. Thanks, Melissa.
I come from a family of criers, so I'm going to do my darndest to get through this. My sisters and I and our extended family are very grateful. I would like to thank Dean Walker, the faculty, the staff, and students of the college for their dedication to honoring not only our father, but the faculty who received this award and carry on an excellent tradition. We would also like to extend our congratulations to Dr. Bekker. Wow. You brought me to tears. To Dr. Bekker for receiving this award. We understand completely the dedication to scholarship and teaching it takes to be awarded this honor. I'm especially grateful to be representing my sisters. I am the fourth of 6 girls, no boys, and a proud graduate of this college for both my undergrad and graduate degrees. Go Cougars. This campus has been our family's home since 1967, when our parents moved their 6 girls from Southern California to live in the Tree Streets, just east of here. Our father had turned down an administrative position at the University of Arizona to come to BYU, where he fully expected to be a professor of political science and live out his years teaching, mentoring students, and researching his way to tenure and quiet retirement. However, life never goes as planned, and within the first 18 months, he was associate dean and then quickly dean. He accepted these positions with the understanding that he would be able to continue to do what he loved most and to teach a class each semester, either international relations or constitutional law, which he did throughout his 17-year tenure as dean. Our father's dedication to this university was an example to each of us. He believed that BYU would be an example to the world of the merging of scholarship and faith, and that those two goals did not live independent of each other. It's difficult to cull down into a single story the lesson from a parent. I have chosen just one example of his lasting legacy in my life. During World War II, our father fought in France in some of the bloodiest battles of the war, an experience he rarely spoke of, with the exception to say that when we complained about something, he would say, "Dear," he always called us dear, "Dear, until you've spent 3 months over Christmas with no shower and in a foxhole, you don't have it so bad." One day I asked my father why he didn't hunt like my friends' fathers. He said to me, "Dear, I have seen enough killing in my life." It was from his experience in the war that he began to develop his belief that diplomacy should always be tried first and that war was the last option. He instilled in us a deep love for our country and that the freedom we had must be nurtured and respected, and that we must be active participants in our government by voting, no matter how much we believed our vote didn't count, and that we must always listen to understand before we can ever be heard. Sorry, I have to pull up my phone for a second. In closing, I would be remiss if I did not honor our mother on behalf of our father. She was his rock. She was the rock of his foundation, his beginning and his end, and he would not have wanted it any other way. I'll leave you with his words. This is from the dedication of his book on David Kennedy. Lastly, and most importantly, I am grateful for the sustaining presence of my wife, Joanne. Not only has she believed in me and in the project, but she has read every word of the book with less concern for my ego than with improving my work. She nursed me through a heart attack that delayed work on the book for 3 months and has fended off demands on my time that would have slowed my progress. There are debts that can never be repaid, but can only be acknowledged, and I'm grateful for the chance to acknowledge my debt to her that I cannot repay. Thank you.
It's my privilege to introduce Dr. Matthew Bekker to you today. Dr. Bekker is a professor of geography in the Department of Geography, obviously, here at Brigham Young University. From the time he arrived here at BYU, he's been a vigorous researcher. Dr. Bekker's chosen field of study, that is dendroclimatology, is a difficult field in which to publish, and yet Dr. Bekker has been very successful, with papers in prestigious journals such as the Holocene, Physical Geography, Plant Ecology, and the Journal of Geomorphology. He's also spoken at many conferences, has produced several professional reports, and written multiple encyclopedia articles. He is an authority in his field. Dr. Bekker is also active in professional associations. Related to the research he will discuss today is his membership in the interdisciplinary Wasatch Dendrochronology Research Group, of which he's a founding member. The goal of the group is to improve our understanding of climatic controls on precipitation variation and thus provide more accurate assessments of risk to water resources in northern Utah from extreme events such as drought and flooding. You're all aware that the dust from the lakebed of the Great Salt Lake poses an increasingly large health risk as the lake dries up. Dr. Bekker's work is relevant here, as it includes stream flow reconstructions spanning 1,000 years for the rivers feeding that Great Salt Lake. Like any geographer, Dr. Bekker has broad research interests. Not only does he work to reconstruct climate, but that work also includes the mechanics of forest ecology, and he has also found a place in historical archaeology, an example of the latter. A seismic upgrade to the Salt Lake Tabernacle at Temple Square was initiated in 2005, and it required the replacement of the wooden beams with steel beams. Dr. Bekker was permitted to study those timbers and thus helped write the history of the tabernacle's earliest construction. Dr. Bekker is an excellent teacher. He's a highly regarded student mentor. Formerly, he has also served as an instructor in both North America and African field schools. Dendroclimatology in Africa's forests presents baffling problems of both methodology and interpretation. Dr. Bekker and those with whom he works are pioneers in that endeavor. Now, he does have a family life. He's got a life besides all of this. If you can't find him in the classroom, if you can't find him in his laboratory or wandering aimlessly in the forest, drilling holes in trees, you may find him birding, attending a baseball game or listening to music. Even so, his favorite place is his home. His favorite people are his family. He's been married to Kathy Clementson for some 29 years now. They have 6 children, evenly split between boys and girls. and they range in age from 27 to 11. Clearly proud of them, Dr. Bekker instructed me not once, but twice, not to forget his 2 grandchildren. In conclusion, I promise that when you leave here today, you'll consider your time listening to him well spent. Dr. Bekker.
Thank you, Perry. Your mentioning my grandchildren relaxed me more than anything else I tried to relax myself with today. But thank you for that introduction. Perry is one of those people you want on your team, and I'm fortunate to have had him as a mentor as an undergraduate. I'm not sure he wants you to know that, but he was instrumental in my decision to not put off graduate school for a year, and because he knows that it usually doesn't happen if you put it off for a year. So thank you for your mentoring. I wasn't going to say this, but I think I will anyway. When Dean Walker and Dean Dufour asked me about this award last year, I said, yeah, I'll accept it, but 2023 me isn't going to be very happy about it. And I can honestly say I'm not very happy to be standing here right now, but it is an honor, and I thank the Hickman family for it, for providing this. Thanks to the college and department for all of their support and friendship, and for sharing your scholarship. What I'm presenting today really could not have been accomplished without a whole bunch of students too, so I want to mention them. I'm going to be talking about a lot of very difficult tree ring analysis and some very difficult species, and some of these poor students had to start dendrochronology analysis on Utah juniper, and that's awful, and I was very mean to do that to them. But I'm actually jealous of them. I love being in the lab, I love working with the wood, but I know that I can't be there all the time, so I appreciate their efforts. And lastly, I definitely want to mention my family. It's great to have them here. Okay, should have said that at the end. If you've spent any time in Utah, I think you can appreciate this quote from Wallace Stegner, that water is the true wealth in a dry land. And you also know, having spent some time here, that the people are where the water is. Specifically where the snowpack is, and as that snow melts in the spring, it provides the water that we need. We live in the second driest state, and we're growing quickly. That water is not distributed evenly spatially, it's also not distributed evenly temporally, at both seasonal and annual and decadal time scales. We have a Mediterranean climate in Utah, which means we get our water in the winter when we don't need it so much, and we don't get our water in the summer when it's sunny and hot and dry and we need it and we want to grow things. So we are dependent on, we are dependent on water storage and water delivery. And that water is also variable over longer time scales, annually and decadally. This is what things looked like last fall. We had extreme and exceptional drought in the state. This, very nice water year that we've had, very nice snowpack that we've had this year, has improved things. We've gotten rid of the exceptional drought category, but we're still in an extreme drought. So I want to emphasize that even one really good snowpack year like this one does not take away a 20-year drought. Most of the last 20 years have been very dry. Some people have referred to it as a mega drought because it has lasted for decades and has also been very severe in terms of the magnitude. So Lakes Powell and Meade are both at record low elevations, and in fact they broke those records 4 or 5 years ago. The lowest that they've ever been since they started filling, and particularly low in June of last year. So if you are a water manager, so my brother, who's the one of my siblings who's not here today, spent several years in radio. He got the deep booming radio voice, and I got this little pinched froggy voice, and yet I use my voice every day anyway. So if you're a water manager, this is the problem you're faced with. You've got spatially variable and temporally variable water resources, and we all demand it and we want it immediately at the touch of a button. So the problem is, if you're a water manager, do you have enough information about past extreme events, droughts in particular, to be able to have a really, to properly assess risk? Can you really say what the biggest drought would be or what the longest drought will be in the future? Well, the problem is we have instrumental records that tell us something about that, but they're relatively short. We had a couple professors in our department who started a weather station on BYU campus a little over 40 years ago, and it's wonderful to have those 40 years of data. We can see temperature trends, and we can look at precipitation and snowfall and so on. And then there are other weather stations like this, and we have a pretty good network of weather stations. And these weather station data have been compiled into databases that you can access. And if you look at those databases, they go back to 1895, and that looks great, until you realize that most of those weather stations maybe go back 40 years. And so we don't have a very long instrumental record for a lot of our variables. If you look at stream flow, you have the Weber River record from the USGS in the upper right. That is our oldest stream flow record. It goes back to 1904. So we have more than 100 years of stream flow record for the Weber, but is that even enough to be able to really help us assess risk properly? What can help us then is dendrochronology. As Dr. Harden mentioned, dendro for tree, chronology for time. These are biological organisms that depend on water, just like us. But the difference is they live longer than us and they have a better attention span. And they record climate, and most often they record water faithfully. Narrow rings for dry years, wide rings for wet years, if you're in a place like Utah, where it's relatively dry. So because of that longer record, and because they depend on water for their survival, we can then use these as a way to extend our record further back in time and use that as a proxy. I'm going to spend a little bit of time here giving you some background on dendrochronology. I would be happy if I could just spend the whole time talking about this. I really prefer getting into the wood and working with the wood itself. So some of these basic principles, one of the principles is the principle of site selection, and von Liebig's law of the minimum. And putting those two things together, we can look at a tree ring width and we can decompose it into one of only a few factors. Simple age, age-related factors, simple geometry, which is actually not of interest to us and something we have to remove from the data. And then climate, which could be water, could be temperature, and then internal or external disturbances to the stand. Liebig's law of the minimum states that there will be one factor. There's a lot of factors that influence tree growth, but there's one factor that's going to be most limiting to growth. And if we can select a site that will limit the factor that we're most interested in, then that's going to come through in our analysis. This is a very low elevation, very steep, rocky, south-facing slope in the Wasatch Mountains. And I have transversed that slope with a chainsaw on my shoulder, looking for tree rings. And the reason we were on that very steep slope, putting our life in our hands, is because we wanted to reconstruct climate. And if you have a site like this, where there's basically no soil development, and it's very hot and very dry, the ring widths are primarily going to reflect water availability. And we can minimize then the disturbance because these trees are not close to one another. There are no fuels to carry a fire. You could have a rock fall here and there. But mostly the disturbance effect is going to be minimized and the climate effect is going to be maximized through site selection. So this is actually one of the trees from this site, and there's two very narrow rings here representing dry years and one very wide ring here representing wet years. The second important principle in dendrochronology is cross-dating. We don't simply count the rings. It would make my life a lot easier. But we take a small core sample, and we do not kill trees, at least we try not to. We are mean to them, we do drill holes in them, but it's a very small hole, and most trees, like these conifers that we're working with, will heal over that very quickly and not have any negative response to it. We take those core samples and then we compare several samples across a site, several samples in several trees across a site, and we look at the patterns of wide and narrow rings and we match those up. So we're cross-dating the patterns, not just counting the rings. And the first reason for that is because either the tree can make a mistake, and I'll explain more on that later, or we can make a mistake in our analysis, our measuring, and our counting. So we pay attention to these patterns of wide and narrow rings, much like a barcode, to get an idea of how the trees are responding. Well, we know the trees are responding to the same environmental factors, and the fact that that happens means that they have the same pattern. And so we're able to be certain in our dating. Dendrochronologists are really excited about the fact that they have annual resolution in their data. We're not like geologists with this plus or minus 50-year stuff. We have annual resolution. And if we can't prove that, then we've got a problem. The second reason, though, that we cross-date is it allows us to extend the record even further back in time. So trees can be much older than humans, as I mentioned. Here's an 1,100-year-old tree right here. But there are also dead trees that can stay on the ground for a long time and not rot. So this is an 1,100-year-old tree here. This is a 700-year-old tree here. It has 700 rings in it, but it also died 300 years ago. So by taking a sample from this tree and a sample from this tree and matching those patterns together, we now have a 1,000-year record with a sample depth of 2, and then we keep sampling more trees. And using living and dead trees together, we're able to build that record further back in time. It's pretty rare to find a 1,000-year-old living tree. They are out there. But the dead wood can hang around for many centuries, and that allows us to extend that record even further back in time. So we're trying to get a better perspective on water resources, and dead trees allow us to do that even better. Okay, so before I dive into water, I just want to show you some of the breadth of applications. Geographers tend to be people who are interested in a lot of things. I always say easily distracted. I'm a physical geographer. I'm pretty much interested in anything in the natural world and how it connects to humans. And then dendrochronology makes that even better, because then I can study all these different areas of the physical world, the natural world. But I'm also interested in some things that connect directly to humans, like water resources. And Dr. Harden mentioned my work on the Salt Lake Tabernacle. Historical archaeology has been kind of a side interest, but lately I've had more and more opportunities, and it's fascinating work. I'm just going to go ahead and jump down to these three, though. Earlier I mentioned the site selection principle in dendrochronology, and mostly with water resources we're trying to maximize that climate signal. With these three examples, we maximize the disturbance signal. We maximize trees that have experienced a flood or a fire or an earthquake, and that gets recorded in their growth. And if you choose a site where an earthquake's happened, then that's going to dominate the growth for some period of time, more so than climate. Okay, so if you notice some of these years, this was earlier in my career, and kind of jumping around to a lot of different fields. And also there are a couple of solo efforts here. The last 10 years have been quite different. I've been very focused on water, and also it has very much not been a solo effort. I started getting interested in water resources and attending some conferences and workshops to learn more about that. And then I found out there were a whole bunch of other people at Utah State and other places who were also interested in doing this kind of work in Utah. And so we got together and had our own workshops and came up with this group. And the most important part about having a research group is to have a clever acronym. So we are the water group. Because we want to study dendroclimatology and try to learn more about past variation in water resources. Just to point out a couple of people here, you're going to see Justin DeRosa's name a lot. We are the two kind of in-house dendrochronologists, and we've been mostly focused on streamflow reconstructions. Rob Gillies is our state climatologist, and he and Simon Wong have handled most of the climate stuff. And then I want to mention Seth and Tim over here. These are what some people would call information brokers. I'm going to use that term later on. People who understand the science that we're doing, but they also really understand water management, and they know how to bridge that gap. And so they've been really important as part of this team as well. But everybody here has been important. We all have different areas of expertise and interests, and we've been able to really push this idea forward of understanding water resources a little bit better through dendrochronology. Okay, most of our time has not only been spoken, the area of climate that we have been most focused on is stream flow. And first of all, because that's the one that's of most interest to water managers for water management. It's where we can make the biggest impact on management of this precious resource. But it's also convenient that stream flow is a nice integrator of several different climatic variables, just like trees are. And I want to point out here, we are not sampling trees down here by the river. You saw that steep, rocky, south-facing slope I showed you before. We sample trees up on those steep, rocky, south-facing slopes at low elevations. They are integrating climate factors, and so is the river down here. So there's not a causation here, but there's a strong correlation, a strong, robust, although indirect relationship between them. Now, we are not the first people to use tree rings for climate reconstruction. This has been done for decades, and there have been a lot of tree ring chronologies in blue here that have been developed over those years. But notice that almost all of them are outside of the Great Basin, and almost all of them are outside of the Great Salt Lake Basin. I zoom in a little bit. These are the chronologies that our group has added over the last several years. There's about 30 of them shown here. This is actually an old map. We've added something like 40 or 50, I think, total, within or just outside of the Great Salt Lake watershed. And when I say sites, I mean an area that has 20 or 30 trees that we've sampled, and we usually take more than one sample per tree. So 40 or 50 samples at all these different sites that are then combined together to tell us about water resources. That's it for that. So our first challenge was that we needed to collect some of our own data. I knew that I was forgetting something. The other problem, this is probably the biggest weakness with dendrochronology, is we can extend the records way back in time, and that's wonderful, but the trees don't continue to tell us how they're growing after we've sampled them. After we've sampled them the next year, those data are already out of date. And if we want to say something about this water year or the next water year, the one after that, we've got to go out and sample those trees again. So not only are these existing chronologies outside of where we wanted them to be, they're also out of date. And by the way, ours are now too. Right? So it's a constant problem. But a second problem that we faced was we had looked at work that other people had done, and we knew some of the species that would be best to work with for climate reconstructions. And pinyon pine was one of those. But there's not a whole lot of pinyon pine inside the Great Salt Lake watershed. There's some, and we've used it a little bit. And this is true for other species as well, such as ponderosa pine. So some of the best, so we're starting to understand that's why people haven't done much work in this area is, okay, we got some problems here, right? Well, that kind of forced us into Utah juniper, which I mentioned earlier. Justin and I had both been warned, stay away from Utah juniper, avoid it like the plague. I mentioned the possibility of trees making a mistake, and I'll explain what I mean by that. Under really extreme circumstances, trees will not even form a ring in a given year, or at least they won't form a ring around the entire circumference of a tree. We call that a missing ring or a locally absent ring. So if we're interested in annual resolution and the trees are going to throw us off by a year here or a year there, we've got a problem. So what we have to do is collect a whole bunch more samples. Not every tree will have a missing ring at a site, and we can use cross-dating to identify where those locally absent rings are. The bigger problem that we had heard about with Utah juniper was false rings. So the red line here and the red line here is one annual ring, and there's a false ring in the middle of it. So the tree started to shut down its growth, and then it started up again. It's especially common in areas where you get kind of a late burst of water in the summer and fall, such as you have with the North American monsoon. And we get a little bit of that effect in Utah. So we were told, stay away from Utah juniper. You don't want to touch Utah juniper. But Utah juniper is everywhere in northern Utah. It's really old, and it grows on these super harsh, steep south-facing slope, rocky sites. So it's got really, really sensitive climate response. So as I tell my students in my natural disasters class, if you're careful enough, nothing bad or good will ever happen to you. So we were willing to stick our neck out a little bit and say, we're going to try it anyway, even though we were told not to. And we've ended up adding a new species for dendroclimatology. And we've ended up having some really, really nice records of climate that we wouldn't have been able to get otherwise. So we have focused on Utah juniper. And some of these pieces of wood people would dismiss as firewood. It's wonderfully valuable data to us. So the Utah juniper sample there. I want to mention bristlecone pine. So bristlecone pine is the oldest known living species. Living individuals have been found that are 4,000 or over 5,000 years old. Still pretty uncommon. We have lots of bristlecone pine in Utah that is between 1,000 and 2,000 years old. So we have living trees that are that old, but we also have dead wood on the ground, and bristlecone pine is very resinous. It does not rot very quickly. So we found this piece of wood on the ground in the Price Recreation area down the Highway 6 that goes back to 1333 BC. So it's the first time, we were all very excited about that. This is the first time we had worked with 3,000-year-old wood. So it's fun to discover this kind of stuff, but it's not just that, hey, we just found a really old piece of wood. It's valuable for climate. So we've been working with the remnant wood, pushing that back as far as we can, and I never finished my thought on bristlecone pine. Bristlecone pine can get to 4,000 or 5,000 years old, but these tend to be at very high elevations, and they're responding more to temperature than they are to precipitation. So in order to get bristlecone pines that are responsive to moisture, we had to go to lower elevations. And we found bristlecone pine at lower elevations that had mostly been ignored before. And these are sensitive to precipitation and useful for reconstructing stream flow. Okay, so with all that in mind, we take many trees at many sites and we put those together as predictors in a regression model, sometimes simple, sometimes multiple regression, depending on the strength of the relationship, sometimes principal components. And the methods here, the statistical methods, are very well established in dendrochronology. I'm not going to go into the details, except to say that once we establish that model, so the instrumental record is in black here and the tree-ring record is in blue. So we first of all look at correlation and R-squared, but we also have a very rigid calibration verification procedure, split calibration verification. We take half the record and we use that to predict this half, then we use this half to predict that half, and these statistics are measuring how well we're doing with that, and they're very difficult to pass. Anything above 0 is a pass on this statistic, and so this worked quite well. So once we have this strong relationship built between the instrumental record and the tree ring record, we then use the tree rings to take us back in time. These are our 4 published hydroclimatic reconstructions to date. And if you follow the dates here, 2013 to 2015, you notice we got older and older because we're finding older species. And this is where we discovered Utah juniper and doubled the length of our reconstruction. So we've been able to reconstruct Logan River flows, that's a tributary of the Bear, the Weber River, the Bear River, and Great Salt Lake levels. And that's where we are at this point. I want to focus in on the Weber because this is the one that I led, and I'll talk more about the Provo in just a little bit. The Weber River is one that's very important for municipal and industrial use, M&I use. And so we really wanted to be able to make a contribution to water management here. This is a river that is very important not only for Salt Lake County, but for other parts of the Wasatch as well, municipal and industrial. This project was supported by the Bureau of Reclamation because they recognized the value in supporting this research. So we didn't just want to say, here's your graph, water managers, here's your data, you figure out what to do with it. We wanted to be able to really make a contribution. And we've had some colleagues who have really focused in on how to make those contributions better. They put a handbook together on how to kind of bridge the gap between science and management. And a couple of things that they suggested. Consistent ongoing interactions. So we've had regular workshops with water managers, surveys after the workshops to make sure that we were meeting their needs. They also suggested co-production of knowledge and products. So it's not just us providing them with data, but they're providing us with data, and we have this interaction. And the last thing that they mention in here that I want to bring out is that an information broker is also key. So the two that I mentioned in our research group are people who understand water management, but they also understand science, and they can act as a liaison between us and help us accomplish more. So one of the things we did is tried to present the data to the water managers in a way that would be most useful to them. So water managers of the Weber River had to endure this drought, this 5-year drought, 2000 to 2004. And then the question is, what about other 5-year droughts in this reconstructed record that were similar or maybe a little bit worse? How would their operations have to have been different if they managed this drought versus that one, or this one versus that one? So they've already experienced the 2000s. What about things back in time? What was even more satisfying, though, is when we found out that Central Utah Water was actually using our data to develop their own models and to improve their own models. So this is a hydrologic model that included historic record, so they've oriented the years here from driest to wettest, and includes the instrumental record, and then how much worse would things be with the reconstructed record in the green, and they also put in climate change impacts on top of that. So used our data and then their own models that they'd already developed, they've already worked with to improve those models. And then our information brokers developed this model of reservoir storage. So they looked at 7 reservoirs in the Wasatch, and if we were to go back in 1429 and we had all those reservoirs, what would happen with those reservoirs over time as they experienced these different droughts? Okay. So a nice example of water managers actually using the data and it doing some good with water management. So I've mentioned that we've reconstructed the Bear and the Weber and Great Salt Lake levels, but I haven't mentioned the Provo yet. And that was actually the first river that we wanted to reconstruct. So the Provo flows into Utah Lake and then flows into Great Salt Lake via the Jordan River. Before it makes it to the Jordan River, though, there is a pipeline that takes water from Utah Lake straight to Salt Lake City, where the biggest population is. So another very critical river for municipal and industrial use. But there's a reason why we haven't done the Provo yet, and that's because it's a mess. Some of the other rivers that we've looked at, we've been able to get so-called clean stream flow data, that is, one that's free of diversions. It's actually representing climate rather than human influence. But the Provo has lots of transbasin diversions from the Colorado River through the Duchesne Tunnel, from the Weber River through the Weber-Provo Canal. So we taking water from other basins and putting them into Provo. Why? Because it comes down here and then is transferred straight to, here it is, straight to Salt Lake City via the aqueduct. And even the headwater lakes in the Uintas are not natural. They've been turned into reservoirs. So it's very difficult to get clean climate data here. And we actually had to meet with a very long-time commissioner for the Provo River who was about to retire. He did not have graphs of data or websites. It was all up here. And so we had to sit down with him and go through these different diversions and figure out how to correct them and which gauge should we use. We were going to use a gauge that used to be here, and now Jordanelle Reservoir is there, so they had to move the gauge over there. You don't really want to use the gauge that's been moved around. So we chose a different gauge after talking with him. So basically, again, practitioner knowledge, communication between science and management is key to pull this off. We have successfully reconstructed the Provo River, and we have been able to go back about 1,100 or 1,200 years because we have these older trees now. Now the question is, if we have long records for all these different rivers, can we make some connections between the different basins? Get to that in just a minute. This is another look at how the instrumental record compares to the reconstructed record, kind of graphic that might be useful for water managers. Just point out 1987 to 1992 is the worst 6-year drought on record. 2000 to 2004 was the worst 5-year drought on record. Usually when we do these reconstructions, the reconstructed record is a lot worse than the instrumental. But for the Provo, these instrumental records were also pretty bad, and that tells us that something's happening in these most recent years to change the situation, and it's all part of this mega drought that we've been in for the last 20 years. So our next step, and I just got these data last week, but our next step is to look at some cross-basin comparisons. The Bears are furthest north watershed, the Provos are furthest south. When do they line up? When do they match each other? When are they in sync? When are they out of sync? And then the next step would be to try to explain why that is. Just want to finish up with a few ways that the data have been helping with other efforts. So Rob Gilly, Simon Wong have had this Salt Lake prediction model in place for several years now, and it has successfully predicted changes, upturns and downturns in Great Salt Lake levels about 5 years in advance. And our tree ring data actually improved the strength of this model. And this is an ongoing effort. If you look at the Utah Climate Center, you can see more about this work that they're doing. Some other work that is ongoing. I'm working with anthropologists both at BYU and at Utah State with this project, analyzing the hydroclimatic context for Fremont cultures. We want to cover the time period 300 to 1300 AD. That means we need 2,000-year chronologies. So we're happy with our 1,000 and 1,200-year chronologies, but now we're trying to push that back and build some 2,000-year chronologies to be able to support projects like this. Kind of the future, where I'm headed next is quantitative wood anatomy. And this is something that's been done for quite a while in Europe, but North America has been a little bit slow to catch on. But I went to Switzerland on my sabbatical a year ago last fall to learn quantitative wood anatomy. A very, very long, tedious process to prepare the samples to be able to look not only at the rings, but to look inside the ring at the cells, and not just measure the ring, but measure the lumen area and measure the cell wall thickness. And I'll skip my particular application here for time, but a very different view and a more mechanistic connection between what's happening with the tree, the tissues, and what's happening with climate. And I should mention that the people in Switzerland have not only developed all of this equipment and the expertise to have really, really good, high-quality wood anatomy images, but they've also developed software that will automate the process for you. So no, I am not going to count cells like I count tree rings. The machine does that for me. There are other North American scholars who are also getting into quantitative wood anatomy, and I'm working with them in the greater Yellowstone ecosystem, for example, to develop not a millennial length chronology of tree rings, but a millennial length chronology of wood anatomy characteristics. In particular, we're looking at cell wall thickness as a more mechanistic temperature proxy. It does a better job of measuring temperature than ring width does, in short. Okay, other future work, well, kind of ongoing in future work. Dr. Harden mentioned that there's not a lot of dendrochronology being done in Africa. These are International Tree Ring Data Bank tree ring sites. Hardly any in the continent of Africa, and yet it's a very important continent climatologically and for water resources. And so last year I attended a field school in Zambia, and we're there not just to do the research, although that is a component of it. We're also there to help build local capacity. We don't want to just come in and do our research. We want to help train faculty and graduate students there who have not done any dendrochronology. We want to come in and train them, help them know what they need to do so then they can do that work and build those chronologies and that research in the field there. So we have an NSF grant in on this. We have an NSF grant in on this work. If I submitted two, maybe I'll get one, we'll see. So that's ongoing work. Oh, and I just heard about a week ago that we got the details for the next iteration of this field school, so I'll be returning this summer to help with the research, but also to help train the next generation of dendrochronologists in this area. To close, I just want to mention a couple of things. Many of you may have seen this press release from Ben Abbott, who's a BYU professor and includes several other BYU scholars, basically mentioning that we need to do things differently with Great Salt Lake. It is drying up. We have toxic dust that's going to get into our air. And we need to do a better job of managing water resources so we don't lose this resource, Great Salt Lake. It's important ecologically, it's important economically, and it's important for our health. So take-home message here, every water user, every manager, every user of water anywhere needs to be on board, all hands on deck to try to improve the condition here. Very last thing I want to mention is I talked about bristlecone pines. We sampled this bristlecone pine in the Price Recreation area and trees that looked like this one that were this old also in this area. Well, there was a fire that burned through here just a couple of years ago, and it burned in the bristlecone pine. There's a reason the bristlecone pine lives to 1,000 and 2,000 and 3,000 years old. It doesn't usually experience fires. So this is not normal, and I want to be very careful because I cut my dendro teeth on fire history, and I know that fire is important for many ecosystems. It's crucial for some, but this is not a normal fire. This is a fire burning in June with late season fire characteristics, very extreme canopy fire that got up and burned trees that haven't experienced fires for thousands of years. So the conditions have changed, climate has changed, and that has changed the disturbance regime. And the problem with that is we have the potential of losing the library. We're losing these 2,000 and 3,000 year old trees that are providing the information we need to better understand climate. So I'll close with that. Thank you. Be happy to take questions.
We maybe have time for one or two questions. Does somebody have a question about the record? I know some of you have class.
Yeah.
What is the flow that's going into the Great Salt Lake it's going to agriculture? Where is that happening?
To some extent from all of the rivers. So the question is, what is the flow that's going into the Great Salt Lake that's for agriculture? All three rivers are used to some extent with agriculture, but primarily the Bear, probably secondarily the Provo, and then the Weber. But all three of those are gradually being shifted more and more towards municipal and industrial and less towards agriculture. Yep. Yep.
Are you optimistic about the Great Salt Lake?
I want to see how people respond to that report. If they respond well, then I'm optimistic. If they don't, no, I'm not.
This is a follow-on. Have you had, do you feel like you've had an opportunity to work with the legislature at all? And are there listening ears?
I have not directly, but Ben has. And I can't imagine anybody better because he's an excellent scientist and he's also very good at explaining the problem and speaking calmly and being able to explain what needs to be done. And he has been asked to come and give some testimony. And so I'm optimistic about that. Okay. Yep.
Why do you have to resample the tree rings every year? Can you, to maintain the model of dendrochronology, like you said, they go out of date. Why?
Yeah, thank you for that. Let me clarify. So nothing happens to the record we already have, but if we want to know what happens this year or next year, we've got to go back and sample those trees again. We can look at the instrumental record, but if we want to know how that instrumental record compares to the trees, we got to go back and sample those same trees again. So my colleague at Denver, who came up with all of these, anyway, the booklet that's trying to help scientists and managers come together, she had a specific request from Denver Water, for example, to go back and sample in 2002 after that drought because it was worse than the year before. They said, oh, thanks for telling us last year. Can you tell us how this year is? So they had to go back out and resample those trees. So if we want to stay up to date with how the trees are responding to climate, we got to go sample them again. Yep.
Thank you again, Dr. Bekker, for this. So a little bit depressing, but it sounds like something for us to all work on together. And I'm constantly lecturing my children about the drought, so maybe I'm doing okay. Right?
Good, good. Keep it up. Make them feel guilty.
Replace my grass with something else, I think is the
Yeah.
We're grateful for for Dr. Bekker. I was calling him Matt earlier informally just because I've worked with him so much on so many different committees, and I consider him a friend. He's not only a wonderful scholar, but he's just an excellent human being, and really grateful that we could hear from him today and for all the work he does. We're grateful to announce our Hickman Scholar for next year, 2023-24, is Dr. Mark Christensen. Mark, you want to give us a wave over there? So, next year, we're looking forward to hearing from Dr. Christensen. He's from the history department, so we'll look forward to that next year. Also, students, I saw some of them leaving, but for those of you who are here, please scan your XP points. Every time you come to a college lecture, you get extra points, and it signs you up for treats and prizes, and we have a grand prize of $1,000 technology at the end of every semester. So if you didn't know about that, students, scan your XP code if you're in the college as a major or minor, and that will take care of that. So again, thank you so much for Dr. Bekker and his family and for the Hickman family. We will end our meeting today with a prayer offered by Dr. Bekker's research assistant, Kyle Bird.